The topic of this lecture is homotopy perturbation method for integral equation. In previous video, we already solved partial differential equation, only ordinary differential equation while using homotopy perturbation method. So let me just construct a theory for integral equation. We write our integral equation in the form f of x plus a to b kxt v of t dt. This is our integral equation. Remember that here the solution is v. Now let us define the linear operator. Since we know that in homotopy perturbation method we first need to define the linear operator. So for linear operator, what we do, we write this integral equation in a following form: a to b kxt v of t dt is equal to 0. When we define linear operator, we also define it like this so that we can get approximate solution. So rather than getting exact solution, we get approximate solution by homotopy perturbation method. So we should define linear operator as a function of u. So we replace this v with u and this v with u as well. Since u is an approximate solution, here u is approximate solution. Now, as we did earlier, we define homotopy function, homotopy of the form which depends on the solution and the parameter p. We have 1 minus p f of u plus p, and here we have L of u. This f of u is the homogeneous, non-homogeneous function. It is non-homogeneous function. This whole term is known as f of u. And this linear operator that we already defined over here, this is our exact integral equation. This is our integral equation. We just have written this in the form of u, which is approximate solution. When p is equal to 0, you get h u 0 f of u. When p is equal to 1, you can see that h is f of, this will be 0 plus L of u. So it means that your solution is starting from p0, where we get u naught, and at the u naught and u1 and so on, other values as well. When p is equal to 1, we get our solution u. Next, we define the solution in terms of perturbation parameter, not perturbation, but embedded parameter, n 0 to infinity, pn un. So this is our solution: u naught, u1p, u2, p2, u3, p3, plus so on. This is infinite series. And we know that from our previous video, we get u naught, u1, u2, and u3 from this equation. And remember that we also need to put this equal to 0. So after getting u naught, u1, and other values, we apply limit p approaches to 1, since we know that at p is equal to 1 we have a solution, and the solution of our original equation, as we saw that when p is equal to 1 we only get this L of u, and this L of u corresponds to our solution, our integral equation. So we get the solution p of x. So this is the theory. So first you need to define function, then you need to define linear operator, write it as the weighted average, weight functions of in terms of p, the weight of 1 minus p and another weight p. And at the end, when we put all these values and combine after comparing the coefficients, we get u naught x is equal to f of x, and then pn plus 1 is equal, pn plus 1 will be un plus 1 a to b kxt unt dt, and n is greater than or equal to 0. This will be our iteration procedure. So I hope you get the point. You just need to replace, or you need to transform your knowledge of ordinary or partial differential equation into the integral equation. Okay. Now we want to see some examples. But before solving for examples, we write, there is one thing that we have to write, which is for the convergence. For convergence, we need to show that 1 minus a to b, the kernel at t comma t and its mod will be less than 1. There is a theory behind that, but I will not prove it over here. You can easily, for example, show that, not probably easily, but using some Neumann series, some concepts, you can show that if this will satisfy, then you get the converge solution. Otherwise, you will not. So now I solve some examples where I will use this convergence criteria. It is similar to the series you have, and you show that this series converges for some particular values of x. Okay, so let me just go to the examples. You need to remember this equation. It is not very difficult to memorize this inequality. Example. Suppose I have an integral equation and we have right hand side x minus t, u of t dt. This is our equation number 1. First, I need to check either this will converge or not. So first we need to check this inequality. To find this inequality, I need ktt. What is kernel over here? Here the kernel is e raised to power x minus t, and ktt will be equal to 1. And what you do, you basically integrate 1 minus a is 0, 0 to 1 over 3 dt. It should be dt. So what we see over here, 1 minus 1 over 3, this is 2 by 3. And if you take a mod, there is no need of taking a mod over here, but since it is positive, so, but anyway, we can take a mod and we get 2 by 3, which is less than 1. So it means that this satisfies the convergence criteria. Remember that this is a convergence criteria. Unfortunately, I did not prove it, but you just have to memorize it. Memorize that. Previously, we saw that we develop a theory where we not solved, but develop a theory for the integral equation. There are two questions, maybe only one question. The question is how to define u naught and how can we define u1, u naught or u1. From the theory, we can define u naught x is equal to 0 and u1 x is 1 by 3 e raised to power x. And the next value is, for the time being, just take these two initial values, these two values, u naught and u1. U naught is coming from the theory, it should be equal to 0. And another value is u1x, which is actually coming from the homogeneous function, non-homogeneous function. Okay. The next value can be obtained as un plus 1 is equal to un minus 0 to 1 by 3 e raised to power x minus t unt dt. That's what we have over here. So what we do, we put all the values. For example, n is 0. You see that we have two guesses in first step, u naught and u1. When you put n is equal to 0, you will get u1. But so what we do, we put n is equal to 1. So we have u2, u1 minus 0 to 1 by 3 e raised to power x minus t u of 1t dt. We put the value over here 1 over 3 e raised to power x minus 0 to 1 by 3 e raised to power x minus t and u1t e raised to power 1 over 3 e raised to power t dt. We solve this equation. We get 2 by 9 e raised to power x. Similarly, when we put n is equal to 2, you get u3, u2 minus 0 to 1 by 3 e raised to power x minus t u2t dt is equal to 4 by 27 e raised to power x. You must be wondering, there is no homotopy perturbation method over here, but I will go back to the theory first and I will explore this example again. So just follow these steps. For the time being, there is no perturbation parameter and so on and so forth, but still we get the answer. So let me just solve this problem first and I go back to the theory. So similarly, we get u4 and u5 and so on. So at the end, u of x will be equal to u naught plus u1 plus u2 plus u3 plus so on. U naught is 0 and we get e raised to power x, taking e raised to power x common, 1 over 3 plus 2 over 9 plus 4 over 27 plus so on. We have put it all these values 4 over 27 over here, 2 over 9 over here, so on. The only thing is left to find out the formula for the bracket terms. So we have e raised to power x n 0 to infinity, 2 raised to power n, 3 raised to power n plus 1, and then we have 1 over 3 as a common, e raised to power x, and 0 to infinity, 2 by 3 n, and when we apply series, the formula for this, ex over 3, 1 over 1 minus the ratio, 2 by 3, and we have 3 over here. We have ux is equal to ex over 3, and the answer is 3. Okay, and at the end we get ux is equal to e raised to power x. So this is our solution. So let me just go back to look at the theory, how this probably has arrived and how we solved this integral equation while considering u0 and u1, and where this formula come from. There is no homotopy perturbation method. Let me just go back to the theory first. Okay, suppose homotopy perturbation method theory. From this theory we get the particular formula that we can use f of x a to b kxt v of t dt. This is our question. Suppose we have L of u. Since we want to change this v with u, we get f of x minus a to b kxt u of t dt. Remember that we are solving this for, we are applying homotopy perturbation method for integral equation of first kind. It is integral equation of first kind. Okay. When we developed the theory from here, it was Fredholm integral equation for second kind. It was a second kind. Now, and the example we saw that this is also Fredholm integral equation of first kind. And for first kind, we developed this theory, which I did not show, but I will prove it now. So suppose we have L of u over here. The homotopy is defined as HUP 1 minus P u of x plus P LU of x is equal to 0. Our solution is u is equal to n 0 to infinity Pn un. This is our solution. And at the end we get v of x limit p approaches to 1, and we apply this on u and 0 to infinity Pn un. This is the final solution. This is the solution that we obtain from homotopy perturbation method. When we apply p is equal p approaches to 1, we get the solution for integral equation. So what I do, I put this equation into the homotopy equation. So how we do it? H u of p, first I multiply these terms. Okay, we have u of x minus p u of x plus p L u of x is equal to 0. Then we have u of x minus p u of x plus p, and then we have our linear operator minus a to b kxt u of t dt equal to 0. We have u of x minus p u of x plus p f of x minus p a to b kxt u of t dt is equal to 0. Okay. So what we do, we put our solution, that is the solution with parameter p. We put this into that equation. We have, for example, maybe I have to put u of x 2 times. I just take a common over here, n 0 to infinity pn un, or maybe I can just put direct value over here, n 0 to infinity pn, and what we have un minus p n 0 to infinity p n pn un. There should be one p pn un plus pf of x minus p a to b kxt n 0 to infinity pn un dt is equal to 0. So just expand it for first few terms. You will see that we get u naught pu1 p2u2. Then we have, when I add these two parameters, I get pu0 pu p2u1 p3u2 so on, plus p f of x minus, I also add this p into that p a to b kxt, and I have, for example, pu0 p2u1 p3u2 so on, dt is equal to 0. That's what we have over here. Okay, if you just take a look on the coefficient of p0, what we have a coefficient of p0, and there is no other coefficient of p0, so this u naught is equal to 0, and that's what we had over here in the equation. Okay, next, when we have p1, the coefficient of p1, here we have, for example, u1, then we have minus u naught, then we have plus f of x, and we probably get some equation from here, but since u naught is 0, so we get only these terms. u naught is 0, we get u1 is equal to minus f of x. That will be over u1. If we continue this way, so you can see that, for example, in this example, we had u naught is 0, and then after some manipulation we can write u1 is equal to plus 1 by 3 e raised to power x. In the theory it is u1 minus f of x. We will see that how we can accommodate this minus. Then we take coefficients of p2. We have u2 that is coming from here. Then we have coefficients of p2 over here, minus u1, yes, minus u1. Then we have coefficients of p2. These are coming actually from this integral. So we have minus a to b kxt, and we have u1, I think we have p2 u1, yes, dt, and that will be equal to 0. And from here we have u2 u1 minus or plus a to b kxt u1t dt. Here we have all the terms over here. Okay, so that's what we have in general. In general, I can write this as un plus 1 un plus a to b kxt unt dt. Okay, so that will be the formula, general formula. So in general, we have u naught is equal to 0, u1 is equal to, it is written minus f of x. You can, in fact, what you can do, you can in fact write this as maybe L of u a to b minus, sorry, kxt u of t dt minus f of x. If you define your linear operator like this, then you will get this term, which I write it over here. u1 is minus f of x, and we have un plus 1 un plus a to b kxt unt dt. This is the case when we have linear operator defined L of u f of x minus a to b kxt u of t dt. But if you have an operator defined as a to b, just try it yourself, u of t dt minus f of x. In that case, you might get u naught is equal to 0, u1 is equal to f of x, and un plus 1 un minus a to b kxt unt dt. That will be your formula for solving this first kind integral equation of first kind. That's what we used over here. Just try to do it in different ways. That's what I already explained. You can probably consider LU like this, or maybe LU like this, right? So that was all about the homotopy perturbation method for integral equation. Unfortunately, I solved example first. First I solved the example, then I developed the theory. I think you need to check the theory before going into the example. Thank you for watching.